Thank you. It's my pleasure to have an opportunity to speak this afternoon. And I'm going to talk about another part of the world and relate it to what's going on in the higher latitudes, but in the tropics. And I want to start by pointing out that it's a team effort that we have, and that team is international. And we've worked to recover these archives in 15 different countries, and it would not be possible without that international assistance. So here are my main objectives. I want to talk about the importance of the tropics and tropical glaciers as recorders of climate and environmental change. I want to introduce some new records that we are developing and present these glaciers as our most visible evidence of global warming that we have on the planet. Things we know with certainty from these observations. Very few things in life we know with certainty. And things that on evidence seem probable. And evidence for abrupt change, both past and present in these different parts of the world. And then this very important thing is getting a time perspective of the change, to be able to put it into a longer time perspective. And then, depending on how my time is going, some closing remarks on human response. So, if you look at the take-home message up front, we've been working on these glaciers for 30 years. And I took this photo in 1977 of the margin of the Quelccaya Ice Cap. It's in the Andes of Peru, about 18,600 feet in elevation. And it very nicely shows this very distinct annual stratigraphy, because there's a very wet and dry season in this part of the world, and you can see how you could recover that record. The photo on the right was taken at the same place in 2002, and you can see that not only is the ice retreating, and we're losing that ice, but we're also losing a valuable record of our past. If you haven't seen an ice core, this is what they look like. This is drilling at 20,000 feet on Las Caran, down in the Andes of Peru. And these cores are brought back frozen, and they archive a large part of the environmental variability. These are some of the parameters that we measure. And the beauty of them is that they look at the climate, things like temperature and precipitation, but you can also look at forcings like volcanic activity. You can then look at the anthropogenic emissions. You can look at the gases trapped in the bubbles. And you can also look at vegetation changes, particularly in the tropics where there's vegetation in these regions. So it's really a multidisciplinary type of study. And the laboratories, Class 100 clean room for the chemistry and the dust measurements, mass spectrometers for the isotope measurements. And one of the things that we have built is a storage facility. We now have 7,000 meters of core stored at minus 30 degrees C in this freezer. And when we started this, we didn't realize how valuable this archive would become. It's the only tropical collection in the world. And as these glaciers disappear, in the not too distant future, this is the place where you'll have to come to find a representative piece of ice from that part of the world. We also design and build our own drills to recover these cores. And probably one of the most important ice core records that just came out in Science in November was this Epica core, which shows the long-term perspective of some of the greenhouse gases, CO2 in red here, methane, nitrous oxide, and the temperature of the planet. And you look at that long-term perspective, and you can see, if you're looking at something like CO2, that during the cold periods when the glaciers advanced, CO2's dropped to 180, 190, then it gets up to approaches 300 parts per million by volume. But then you look at both in the CO2, you can see how unusual where we are in this 650,000 year perspective, both when you're looking at CO2 and methane. So that perspective is very, very important. Now the tropics are a very important part of our planet. And you have to remember we live on a sphere. And because of that, 50% of the surface of this planet is in the tropics, between 30 north and 30 south. If you look at the zonal distribution of annual precipitation, you can see that now that's centered just north of the tropics, about 5 degrees north of the equator. And you can see the intertropical convergence zone and the higher latitudes, these various zones. The other thing that makes it very important is that we have 6.5 billion people living on the planet. 70% of them live in the tropics. So it's a very important area to understand both natural variability of the past and also future variability. There are other things that make the tropics stand out. One is that if you look at sea surface temperatures that you see in this center panel, and if you look at precipitation, you can see how it follows those sea surface temperatures. But if you go up to the mid-troposphere, where these glaciers are located, what you find throughout the tropics is this uniformity of temperature. You don't find this anywhere else on the planet. And therefore, when you look at signals in this part of the world, and particularly what's happening to glaciers, I believe it's particularly important. And you can actually see how the temperatures move up when we have an event like the El Nino event, where this warm water pool collects off the coast of South America. And this is 4 months before the maximum of the event. This is at the time of the event. You're looking at temperature changes between 1,000 and 300 millibar level in the Earth's atmosphere. And you can see how that within 4 months after this event, that temperature is uniformly distributed around the planet through the tropics. And again, a very important place to look. Now, when you look at a glacier, there are really three things that determine the length of the records and the quality of the record that's preserved. Elevation at which it's located, and which will determine its mean temperature. The colder it is, the better preservation. The amount of snow that falls each year on that site, that'll give you a thickness. And then the thickness actually is very important in your resolution. How far back can you take annual layers? And as far as the length of time, the temperature right here at the ice bedrock contact, if it's frozen to the bed, time can't be removed. So you can get very long records out of places like Tibet and down through the Andes in South America. And I'm just going to show a couple of these sites. These are sites where we have glacier drilled ice cores. This is our next drill site in the southwest Himalayas. And I'm just going to look at one out in the center of Tibet. This is one of the most remote parts of the planet. And if you go out there, there are no roads, there are no people living out there. And there are sand dunes, and these sand dunes move in the spring. And because of that, when you look at the glacier and you look at the archive, there is an annually layered record of the history in that part of the world. And when you go up on these ice fields, you actually walk across these years like steps going up. So they're very good recorders. And when you drill these cores, you can see every spring dust layer. And you can count this back to 82 BC just in the drilling process. So it's a quality of the archive that becomes an issue. There are also other issues of getting these cores back frozen. And just to give you an idea, this is the way they're done in the Himalayas. These are insulated core boxes, and you can get 6 meters into each box, 12 meters to a yak. We generally drill 500 to 600 meters of core, so you can get an idea of the herd that's required for that transport. But the interesting thing is that if you drill these cores and you bring them back, this is the isotope. This is our proxy for temperature, and I'm going to say a little more about that. But this is in the center of Tibet, this very remote part of the world. This is the mean value. And what will stand out to everyone in this room is the enrichment taking place in the top of this core in the last 50 years. And this is a characteristic of all the glaciers in Tibet. So over the last 30 years, we've collected these cores. These are the places where we've drilled. And we've been working on putting together a global picture as it's recorded in these glaciers. This is just north of Arequipa, a place called Corapuna. It's 21,500 feet, so it's right above the Pacific Ocean. And what we're looking at here is long-term history of things like El Nino. These sites are spectacular when you're up there drilling, but they're also spectacular what the ice records, because in this ice you wouldn't expect to find things like insects. But they get caught up in thunderstorms, and they come out in the snow, and they fall, and they're perfectly preserved. Anything that goes in the ice is preserved, and you can identify it, and you can also carbon date it. So you can also verify timescales and the like. So this is very important. I want to talk a little bit what's happening to glaciers. You probably, this past year, there were some attempts to save some ski resorts over in the Alps by putting polyester white cloth across the glacier, which didn't work. And if you watch the Olympics, they were doing the same thing, trying to preserve the slopes because the glaciers are disappearing over in that part of the world. And as a part of our program, as we drill in these different parts of the world, we've also collected photographs of what's happening, and in many cases these have much greater impact than even looking at isotopes, I mean, to the average person. And I'm just going to show a few of these, and I'm sure Gary's going to show some more. This is up in the Brooks Range. This is McCall Glacier. This is 1958, 2003. If you go to southeast Alaska, the Muir Glacier, photo 1941, same place in 2004. This glacier was over 800 meters thick in this valley, and you can see how it's retreated up. If you go to China, the same story. This is glacier number 1 in the Tian Shan, photo from 1960. These glaciers are connected. 1990, they start to separate. By 2001, they separated. Himalayas, 1978, 1989, 1998, 2004, and this is happening all through the Himalayas. And this is a source of some of the major rivers for the Earth and the people downstream. You've heard about the Glacier National Park here in the U.S., and actually it's in the brochure. I saw this, the Grinnell Glacier, and then also the Boulder Glacier here, some people in 1988. Tip of South America, similar story, 1945, 1998. If you go up to Patagonia, here's a photo from 1896, same place in 2001. And then if you go to Antarctica, down in the peninsula, the temperatures here have been warming very dramatically, 2.5 degrees C in the last 50 years. And what's striking about this figure is we had a fellow, John Mercer, in our center, who published a paper in 1978 in Nature saying that the first evidence of global warming due to CO2 increase in the Earth's atmosphere would be the breakup of these ice shelves, and they would progress from the north to the south. He's since passed away, but if you look at the dates on the breakups of these, you can see that progression unfolding. And the thing that has really surprised the glaciologists who study this is how rapidly they disintegrate. And this is Larsen B. This is January 31st, 2002, coming to February 23rd, and then by March 3rd, a month later, it's disintegrating. So the rate of which they change. And of course, the shelves themselves will not, loss of those shelves is not going to cause increased sea level, but what they do serve as is a buttress to the glaciers on land. And this is Larsen B, where it's broken out, and when that buttress breaks away, then that ice can move faster. And in this part of the world, there's observation now show that these glaciers on land are flowing 2 to 3 times faster after the outbreak of that ice shelf. So that impact, and then we heard earlier about what's happening in Greenland, the impact of these this meltwater and the moulins and the water making its way down to the base, contributing to acceleration in the rate of flow of that ice off the land, and of course that contributes to sea level rise. Now, I just came back from Kilimanjaro, and this is what it looked like last month. And the ice here this is 3 degrees south of the equator, so the ice has retreated to the very highest levels of the mountain. And the oldest picture that we could find was taken in 1912. These are the glaciers in 1912. This is a glacier. It's not snow cover. It's actually ice coming down. By 1970, you can see a canyon start to open here. By 2000, it has really retreated up the mountain. If you go up there today, this is what you'll see. It's a remnants of an ice sheet that covered this mountain 100 years ago. The northern ice field, Furtwanger in the crater. And in 2000, when we drilled here, we had aerial photographs flown, and we made a map of the ice so we could compare it to all the other maps that have been made. And if you do that comparison, you can see the light blue here is the ice on the mountain in 1912, and the white areas is the ice in 2000. So you can see how through time the ice has shrunk. And if you actually look at how much ice was there in 1912, it was 12.1 square kilometers, and by 2000 it's down to less than 2.6. So over 80% of the ice disappeared over that period of time. And if you look at all the maps in between and you kind of just connect the dots and project this out to our future, sometime before 2020, those ice fields will be gone. And of course the archive that exists there will also be gone. We have a good idea of what the last piece will look like. But what is startling is what's happened since 2000. When we were there, we put out stakes in front of this ice wall. This is 50 meters high. This is a northern ice field. That whole wall is retreating at 0.9 meters per year. We now have measurements over 6 years showing that. We put stakes on the highest places on these ice fields. This is in February of 2000. This was in 2004. This is the northern ice field. So between February of 2000 and January of 2006, we've lost 2 meters of solid ice from the surface down on the northern ice field. And that's a serious issue when you talk about the archive, because if you're going to look at the history and record it on ice, you need a place to start and a place to end. And to start here in 2000, we used the IB test, the chlorine-36 bomb test, which left a radioactive layer around the world. And that was 1.6 meters below the surface. So had we waited to 2006 to drill, we would not have had that timeline. So the changes are very significant. If you look at the other ice fields, Furtwanger has lost 2.5 meters in 6 years, and the southern ice field has lost over 4.5 meters in 6 years. And this ice field was only 9.5 meters thick in 2000. So you can see how quickly they can disappear. There are other things happening on this mountain that would suggest that a threshold is being passed. This is actually a photo of a lake bursting out of the side of Furtwanger in 2003. There are 10,000 tourists go up here every year. They walk right here. That's their trail. And this is the first time they've observed water flowing on the summit of Kilimanjaro. And ice is a threshold. If you're below freezing, it sublimates. It takes a lot of energy. It takes 7.5 times less energy to melt ice than to sublimate it. And once you get water on the surface here, then you change the albedo, you change the whole system. More energy is taken up. And so we think that the rate of loss here is actually accelerated in the last 2006, and we'll be able to put a number on that very shortly. The other thing that's very telling, the records from this ice field go back 11,700 years. We have 3 cores drilled through the northern ice field. But you can look at the ice itself and see the change. 50 meters of that ice core looks like this. This is what you call normal ice, where you have snow, compresses, becomes firm, becomes ice. The bubbles are disseminated like this. Right in the top, you can see these elongated bubbles. They're about 14, 15 centimeters long. Those only form when you have melting and refreezing taking place. But the point here is, had it occurred in 11,700 year history of these ice cores, you should see it. It should be physically visible in the stratigraphy in the cores itself. So it suggests things there are much different. When we had new aerial photographs flown on February 28, 2006, that's that photograph. This is what it looked like in February of 2000. And you can just look at the changes. This is the northern ice field. You can see how this is in the process of separating, splitting in two. Likewise, Furtwanger here within a couple of months will be totally split in two. And the southern ice field, which you can see here, is greatly diminished in size. We use the same plane, same pilot, same photographer, same flight plan to refly the mountain. So there will be a new map to show that very, very soon. In South America, very similar story. The glaciers throughout the Andes. The one that's best studied is the Quelccaya Ice Cap. It was the first ice cap we drilled. We first went there back in the 1970s. And this is the largest outlet glacier coming off of Quelccaya. And back in 1978, we set up a baseline to observe this glacier, just to see how tropical glaciers behave. This is a photo from 1978. This is about a 4-kilometer ice field. There's a little pond here. This was what it looked like in 2004. This lake now covers 83 acres. It is 200 feet, 60 meters deep, and it didn't exist until 1991. And we have a whole series of photographs and maps showing this retreat, and we're in the process of producing the one for 2005. But if you look at the 2005 photograph, you can see the ice has actually now retreated up out of the lake. This is bedrock that's exposed in this area. So very remarkable change and exponentially increasing in the rate at which that ice is disappearing. So if you kind of look at a big picture of the Earth, we produced this first maybe 5 years ago, and there were some blue spots on here where there were glaciers that were areas where more glaciers were advancing than retreating. And you can see that as we've gone forward in time, it's a pretty consistent story that the glaciers are telling, and it doesn't matter what latitude you're located. So things that we know with certainty, the glaciers are disappearing, and along with them, a very valuable archive. And this is already impacting the ability for hydroelectric power production, crop irrigation, municipal water supplies. If you go down through the Andes, one of the reasons we were looking at the ice on Kilimanjaro is trying to determine how much water being consumed from the wells at the cities at the base of the mountain has its origin from the glaciers on the summit. And then, of course, the loss of tourism. Kilimanjaro is the #1 foreign currency earner for the government of Tanzania. So in Parliament, they're discussing how many people are going to come here if there's no ice. How's that going to impact the tourism in that part of the world? Now, I want to, if you look at the Earth from space, some of these tropical glaciers don't look so big. This is Quelccaya. This is Lake Titicaca. And but if you go down to the surface and you look at this, you can see the drill dome. It's a pretty significant body of the ice for the tropics. And it's a remarkable body of ice because it has our longest annual record of any tropical glacier on Earth. And you can actually see it, I think if you look carefully, you can see the annual layers each dry season. So like over in China, you can actually develop that calendar. And of course, we bring these back, and they're analyzed. And I'm only going to show 2 of the parameters. We analyzed about 12 different parameters. But this is the dust record in detail. This is depth and core, and this is deeper down. Every dry season, you get a dust peak. So and you just count these back. And this record goes back to about 400 AD. The thing that is truly remarkable is that we drilled this. This is the first tropical glacier ever drilled 20 years ago. And it was before we had any way to keep cores frozen. They were cut into 6,000 samples, analyzed in 2 different labs, one in Europe and one in Washington. And then this time we went back and we brought back frozen ice core. And this is the reconstruction, annual reconstruction of isotopes overlapping. The new core is in red with the old core. And this is for the last 500 years, showing how good the dating is and what a remarkable archive that is for a place where we have very few records. Now, what's a bit disturbing about this is that we've now done this at all these different sites in the tropics, and we now can produce composites. And this is a composite of 5 tropical cores where we have annual resolution over the last 400 years. And when you have that kind of resolution, you can talk about precipitation, and you can talk about temperature through the isotopes. The blue curve is precipitation, and the red is the isotopic record over the last 400 years. There is no relationship between precipitation and isotopes in these cores. The isotopes are behaving independently of that. But if you look at the last 100 years, you'll see the precipitation has been average to above average, the blue curve, and temperatures have been above average. And so all tropical glaciers are disappearing. So the driver here has to be temperature. There's something else that's happening. It's even perhaps more telling. This is the top of the 83 core. These are the annual isotope variations coming up to 83. This is the new core. Starting in 1991, melting started happening at the summit of this core. And the water started moving through this fern layer. And you can see how the record is smoothed out in the presence of water. We have a record that goes back 1,500 years. This event, you don't see this event in any other part of this record. So this suggests what's going on there is unusual in that period of time. If you look at the tropics and you look at these ice cores, you have to remember that they represent the periods of snowfall. And so if you're over in Tibet, that is June, July, and August. That's when the precipitation comes into that part of the world. So 80% of your ice record is that part of the year. If you go south of the equator, it's just the opposite. Huge seasonality, but here you're looking at November, December, January, February, the opposite part. And we have the ability now, having cores on both sides, to combine these and look at a composite record. And if you do that, combine these records and these records, the isotope record, for the last 2,000 years, these are decadal averages, this is what you see. And you can see you're coming along, you can see the medieval warm period here, you can see the little ice age cooling, and you can see the unusual nature of the last 50 years. You can see it in the Jones and Mann reconstructions using other types of archives. And in both cases, the take-home message is it's very unusual what's going on in the recent past, at least on this time perspective. And that, I think this is one of the things that the paleo records can do. And you can break these down, and you can look at the cores out of Tibet. This is the sum of the cores in Tibet, and this is the sum of the South American cores. And you can see there are changes, there are differences depending on where you are. But if you look at all of them, what stands out is how unusual the last 50 years are in those records, no matter where they're located. So things that on evidence seem probable, glaciers, especially tropical glaciers, I refer to them as canaries. They're not going to do they're going to have a big impact on sea level, but I think they're very telling what's happening to glaciers throughout the tropics because they're integrators of the climate system. And the global retreat of glaciers at the beginning of the 21st century is driven mainly by increasing temperatures. So I want to conclude by just saying a little bit about what might be possible. As these glaciers retreat, they're revealing things that they've captured. Ernest Chaplin said, what the ice gets, the ice keeps. Of course, he was talking about the endurance, his ship. But it's true about ice itself. And so as these glaciers retreat, there are things being exposed. And I think there's a whole new field here of investigation. As this Quelccaya Ice Cap retreats, this is all new land that's being exposed. And this is a new lake that didn't exist back when we started working there. And if you look at what it looked like back in 1977, this is all a lake in here now. And you see some people here for scale. This is the backside of the lake in 2002. And here's a person. And right here at the base, we found a plant deposit, a wetland plant deposit, 2 meters across. And it's unusual in that it's perfectly preserved. It's in growth position. You can see it here. And the ice wall, you can see, is right behind this guy. The thing that's really surprised me is how fast this ice can disappear. This is 2002. Here's the plant. Here is 2005, same place. Here's the plant. And as it retreats, there are other plants coming out. So you have an opportunity here to sample these plants, to date them. And this particular plant dates 5,200 years in age. So it tells us that margin, that ice cap, hasn't been smaller than today for 5,200 years. Otherwise, this plant would have decayed. And so these are not rare. We collected some 28 different plants over the last 2 years, and we have an array of dates. And the oldest one is 6,500 years. And this shows the array of dates. All the gray areas are where this ice cap is retreated. And we've only been looking on this one site. And you've got to remember, this is happening to glaciers throughout the world. And so it gives us an opportunity to maybe to say something about how unusual this was. There are other things that come out of the ice, like Ötzi, the Iceman. He came out in 1991, and we know a lot about this guy. We know he was shot in the back with arrows. He escaped his captors. He sat down behind a boulder at the top of the Austrian Alps, and he bled to death. But we also know something had to happen pretty quickly after he died. Otherwise, he would have decayed or he'd been eaten. So there had to be a snow event that was big enough to bury him deep enough until he wasn't exposed again until 1991 when he came out of the ice. But what makes him interesting to us is he's the same age as these plants down in the Andes in the southern hemisphere. And so it raises some really important issues about the climate system and how abrupt it can change. And so here I've compiled a number of records. We have a lot more than these. But this is the Huascarán record in northern Peru. This is the isotope record from Kilimanjaro in Africa. This is northern hemisphere insolation curve, methane from the polar cores, and a isotope record from Speleothem in southern Israel. But you can see where the curve here is. They're the lowest methane records in the last 13,000 years, 5,200 years ago. And this happens to be the same time of our plant and the man. And so it raises some important issues about abrupt changes in the natural system. How does our climate system work? How quickly can it go from one mode to another? And can we learn something about the future by looking at these? Can linear forcing lead to these types of abrupt changes in the system? Are there critical thresholds that can be exceeded? And what is the role of nonlinear feedbacks in our climate system? I think these are extremely important issues. Every place you see a red star here is now where we, since 2002, have been able to find dating of this event. So you can see you're starting to map it out. It's a pretty large-scale event. And that type of thing happening in today's world, 5,200 years ago, we may have had 250 million people on the Earth. We now have 6.5 billion. And so I think we need to understand those changes. This is an interesting curve from Jim Hansen about future projections. And this was published in 1988 in the Journal of Geophysical Research. And these were projections of what would happen to the Earth's temperature as we go forward in time. This was with extreme development around the world. This case C, there was a case, this blue curve you see here, if we would really start to mitigate and sequester CO2, start reducing. And then there was a green projection you see here, which was business as usual. The thing that's disturbing about this plot is that the black line is the actual temperatures of the Earth. And if you look at those since 1988, you can see they're pretty much marching along the business as usual projection curve. So we're starting to get down to where there's starting to be some validation of some of these projections that were made back in the 1980s. And I think for that we should be very concerned. So if we look at the loss of nature's water towers, I think you look at glaciers as being that. They store water in the wet season during wet periods and release it during dry periods and droughts. If you look at where the water is located, of course, most of it's in Greenland and Antarctica, over 32 million cubic kilometers. But there's still another 100,000 cubic kilometers located in mountain glaciers. And you say, well, what if we just melted the mountain glaciers? And I know Mark and Bill Qori were talking about some of these changes taking place in the big ice sheets. But if you just looked at the mountain glaciers and you looked at steric sea level rise, you're looking at at least a half a meter sea level rise. And we've seen the glaciers are disappearing in the mountains. And you're talking about displacing over 100 million people. And it raises all kinds of issues. So I want to conclude by coming and talking just a little about human nature and human beings. And you look at these changes and you say, okay, who's going to pay the cost for change in the future? Just coming from Tanzania and seeing what's going on there. And this is actually a Quechua Indian girl at the base of the Quelccaya Ice Cap, lives there. The history says it's these people who are least able and probably least responsible for the changes that will pay the cost, the first cost of what's happening. And then you say, well, okay, what are our options when we look into the future? And I think there are only three. I mean, we can ignore it, and you know, this is using a market model. Forces, we're going to let it take care of itself. And I would say that's pretty much what the path we're on. We could choose to mitigate, where we actually would invest in looking into some of these alternative energies, wind, sun, and the like. And I think adaptation. I think adaptation is already built in. Places like Kilimanjaro, those ice fields will disappear. If you look at the amount of warming already built in the system, you look at Jim Hansen's work, you have at least 1 degree warming already there. And so I've worked 25 years in China, and I think that human nature says we do very well with crises. And it's kind of interesting, in China, there are two characters for this small word, Wei, Ji. Wei, you might guess, Wei means danger, and a crisis brings about the danger. But the second one, and this 5,000-year-old language, is kind of an interesting one, because Ji means opportunity. A crisis brings an opportunity to make things better. Sometimes we, as human beings, don't do very well until we have no choice. But when we have when we're forced to that, we can do very well. And I would give two examples of that. One, I come from Ohio. In Ohio, we had the Cuyahoga River. 15 years of data, polluted. We knew it was polluted. When did we act on this river? When it caught on fire. No choice, so we had to do something. And they cleaned it up. There's walleye and pike in this river now. It could be done. It just didn't have to. And then if you look at soil conservation in this country, you go back to Hugh Bennett. I mean, you don't remember who the politicians were. But you go back to, okay, the Hugh Bennett, father of soil conservation in this country. 1920s, he's in Washington. There's hearings about the poor farming practices. When do we do something about it? 1931, he's in Washington. There's a huge dust storm comes out of Oklahoma. 12 million tons of dust falls on Chicago. He delays the hearing, so right in the middle of his presentation, this dust will reach Washington, and the policy changed 180 degrees at that time. And we need these type of things. But I think for when we talk about the CO2 issues, the greenhouse gases, this is something different. I mean, these gases that we're releasing today will be there 100 years from now. And so if we use this same model and we wait for that first crisis, when do we actually take action? We already have built in a whole series of crises because it's different. And then so it raises issues. Do we have the right institutions? Do we elect people for 2 years, 4 years? They're not looking on this time frame. And then it also raises another very important issue. What would that crisis look like? I mean, it certainly wasn't the heat wave in Europe in 2003, where over 2 months, 49,000 people died. I mean, it was kind of spread out, didn't get headlines. It wasn't the hurricane seasons in the last 2 years. A lot of debate over what's the connection with warmer temperatures and hurricanes. And so you have to ask, well, what is it that would get us all on the same page so that we would bring about some meaningful action on this particular issue? So thank you very much. I'm probably out of time. Are there questions? Yes.
Kilimanjaro Ice Cap obviously raises big questions about that glacier as a source of water for people in the vicinity of Kilimanjaro, at least. And I presume there are similar problems with other similarly situated glaciers. I wonder if you could talk a little bit about the water supply implications.
I think, I think it's a very important issue. If you look at Kilimanjaro, it's amazing. We really don't know how much of the water that's being consumed there, where the sources are. There's a tropical rainforest on the lower sections of the mountain, and there's the ice fields on top. And so one of our purposes was to collect water from wells and springs for tritium dating and for carbon dating, because the age of the water will tell you a lot about the source of where it's coming from. In Tanzania, they're in the middle of a 4-year drought. While we were there, they started rationing electricity because of it's hydroelectric produced. They also started disseminating food, and if the rains don't come in March, there will be mass starvation in Tanzania. There's already quite a bit in Kenya and Uganda and through that part of the world. And these glaciers they serve as kind of the bank account that during these times that water can be released to a system. But as they get smaller, not only on Kilimanjaro but down through the Andes, you're drawing from this bank account, but nobody's putting anything back in, and pretty soon you lose that part of the balance that we have in the system. This place we're going over in southwest Himalayas, there's a town at the base of this mountain. 85% of its water comes from the glaciers, and the glaciers there are all retreating. And that city has been there for 1,500 years. It was on the old north-south Silk Road from India across Tibet. And you wonder how far into the future they will be able to exist if suddenly they no longer have what has been a long-term water supply coming down from the Himalayas. So I think actually trying to answer that question in our research program, and we go out for getting these archives and getting the history. That's what we build our program on. But we're also building another one that has to do with what do you do about it? How do you help these people adapt to come up with something that you could plan that would replace the role of the glaciers have played in the past, storing that water and releasing that water. Is it possible? Yes.
Are there any exceptions to shrinking glaciers?
If you go up in southeast Alaska, the USGS is monitoring 2,000 glaciers. 1,987 are retreating. 13 are either stationary or advancing. But if you look at those glaciers, you see that they're special glaciers. They're surging glaciers. They're glaciers that don't behave directly with the climate system. What is, to me, is kind of disturbing is that if you go back to the late 1990s, Norway and Sweden had advancing glaciers. They were getting more winter snowfall. The snow that used to go into the Alps has had a more northerly trajectory. But starting in 1999 and coming up to the present, they're now retreating at 20 meters per year. And for a while, the precipitation was able to override the temperature change, but it seems that temperatures have caught up in that sector. Yeah. One more.
Just a brief question. I've seen similar photos of retreating places in New Zealand that didn't seem to be in your research. I was just wondering, is there similar research in New Zealand? And if so, is it showing similar results?
Yes, and I think Gary will probably show some. I don't know if he's got any from New Zealand, but the same story is in New Zealand. And on my map, you'd see that it was also red. It's a pretty uniform story, and that's, to me, is what's disturbing about it. It doesn't really matter what latitude, longitude, altitude that you're located. You're getting the same story on the ice. Thank you.